guys, thank you for watching the 9-2 area of triangles section. We're starting with just a regular triangle. The angles are ABC. Side opposite to angle A, we call it small letter A. Side opposite to angle B, small letter B. Side opposite from angle C is small letter C. And we all know that the area of a triangle is half the base times the height. So if I draw the height perpendicular to the side AC, or small letter B, then the area is half the base times that height. Now, let's look at that height for a little bit. We know in this right triangle over here that the sine of angle A is the opposite, which is H, over C, which is the hypotenuse on the left triangle. So if we solve for H, we can find that H is C sine A. Similarly, on the right triangle, sine of angle C is H over A. If we solve for H again, we can find that H could be represented as A sine C. So if we go to our equation and substitute H with C sine A or A sine C, we can notice a pattern. The pattern is that the area of the triangle is half 2 of the sides multiplied times the sine of the included angle, the angle in between. So if we look at side B and side C have angle A in between them. It's the included angle right here. And also if we look at sides B and A, we'll find that sine C or angle C is included. So based on this pattern, if we draw the height even with C being the base or A being the base, we can find the area of any triangle without drawing the height. So we don't have to draw the height anymore. We can use this pattern. Half of 2 sides multiplied times the angle in between. So the area of triangle ABC, they give it the letter K for area. If you remember in chapter 7, we used K for the area of a sector. So they're again using K for the area here. And the area of the triangle is half AB sine C, because of the included angle, or BC sine A, because A is the included angle, or AC sine B, because B is included between A and C. So these are the 3 formulas, but you don't have to memorize them. You can just look at the picture and see that 2 sides and the included angle make the formula. So let's look at an example. So if we have a triangle with sides 7 and 4, this triangle is not to scale, so I know 4 doesn't look like a short side, but 7 and 4, and the angle included is 73 degrees. Find the area. As you can see, K, which is the area of the triangle, is half 7 times 4 times the sine of the included angle. Should give you 13.4 centimeters squared, or whatever units squared, depending on the units given in the problem. So if it was 7 centimeters, then the area is 13.4 centimeters squared. Let's look at another example. In this other example, we're going to be finding the angle. So we want to find all possible solutions for angle L over here, given that K, which is the area of the triangle, is 15 centimeters squared, and N, small letter N, is opposite to angle N, is 5 centimeters, and M, which is opposite from angle M, is 10 centimeters. So we want to find that angle, angle L. And there are 2 possibilities for that angle if we look at our solution, but let's actually work it out and see what happens. So K, the area, equals half of the 2 sides and the included angle, or 2 sides and sine of the included angle. So half of 10 times 5 times the sine of angle L. If you work it out and solve for the sine of angle L, you'll see that half of 50 is 25, and if you divide by 25 and reduce, you'll see that sine L equals 3 over 5, or 3/5. So now we have to remember the previous chapter where we said that sine is positive in quadrants 1 and 2. So I have to use the inverse sine to find the angle in quadrant 1, and then we'll have to calculate another possibility, which is the angle in quadrant 2. So measure of angle L by inverse sining 3/5, or do the arc sine of 3/5 on your calculator. You'll find that angle L is 36.9 degrees. If I take the 36.9 and use it as a reference angle, since it is acute with the x-axis, and put it in quadrant 2, I can do 180 minus 36.9, and I'll get 143.1. So I'll use 36.9 as my angle and also as my reference angle. Let's draw the two possibilities of the triangle now. So the triangle could be acute as the one that I drew on the top, with the angle L being 36.9 degrees, and it could be an obtuse triangle when angle L, or if angle L is 143.1. So we have an acute and obtuse possibilities for angle L. And we wanted to find all possible solutions. Now I wanted to remind you of a few things also for this section. So the first thing I want to remind you of is the area of a segment. If we have a circle and we find the area of this part right here, that's the area of a sector. Now the area of a segment is when we draw a chord and we're just talking about the area of this part here trapped between the chord, which is right here, that segment connecting the two endpoints on the circle. And that area between the actual circle and that chord is called the area of a segment. Now the area of the sector, which is half, or not half, a part of the circle, that entire area, we did it in chapter 7, and we said it's half of S times R, where S is the arc length, the length of the arc over here. And we actually also did S equals theta in radians times the radius. So I want to put a small r here so that you remember that we did it only when theta was in radians. So if I have the arc length and the radius, I can find the area of the sector. Now to find the area of the segment, we have to do K, which is the area of the entire sector, minus the triangle. All of this is actually K and S, and all of this is chapter 7. So you can go back to your notes and look at where we did the arc length. We said the arc length is just the length around the circle, or a portion of the circumference. And the sector is the pizza slice, and the area of the sector was half of SR, and S, or the arc length, was theta R when theta was in radians. So that's chapter 7. And again, to find the segment, or that piece, we do the entire thing, the entire sector, and we subtract the triangle, and then we have the segment. Also, I want to remind you of the tangent lines. Tangent lines are lines that hit the circle at just one point, called the point of tangency. So you see that green line touches the circle at one point, and that point is called the point of tangency. And the tangent line is always perpendicular with the radius, so they always make a 90-degree angle. And that was in GU2, so I wanted to remind you of this because the homework will have a couple problems that need this. Now the homework is page 342, number 1 through 21 odds. Number 17 is quite interesting, but it's not anything that is hard. It just requires a lot of thinking, I think, maybe. I want you to try hard on the homework, and if you have questions, you can ask me tomorrow during class. Alright, thank you. Hope this helps. Bye.